I can share with you some of my thoughts and research on the topic of methane removal using solar chimney and photocatalysis. So yeah, hello everyone from different time zones. So my name is Wei Li, a senior lecturer in chemical engineering at University of Edinburgh here in Scotland. So I'd like to warn you first that in order to cover various questions, so the structure of today's presentation does not look like a normal academic presentation. So it is not very logically organized, and you will find that the ideas will jump from here to there. So hope it will be fine. So first, I assume we all have the consensus on the emergency of global warming and the importance of methane removal. So let's directly move to the first question. So why we think solar chimney is one of the best solutions. So last Wednesday, in Tinzen's presentation, he mentioned several times that solar chimney is the best and maybe the only solution to collect and process air at a large scale. So here he emphasized that we need to collect and process air at large scale. So why do we need to do that? So what about painting photocatalytic materials everywhere? For example, outside buildings, on wind turbine, and on road surfaces, on moving cars, for example. So they can be all a much cheaper way to do so. So let me show you my thoughts on this. So starting from what the photocatalysis is. So photocatalysis starts from a photocatalyst. So it absorbs solar energy and converts it to chemical energy. So the chemical energy can then drive chemical reactions. So for example, here with the help of this chemical energy, so methane can react with oxygen and change to CO2 and water. So this reaction looks simple here. However, it does not happen instantly like a magic, like then methane becomes to CO2. So not as instant, as simple as it shows here. So actually, it involves lots of steps. So I will not go through these steps, just show you how many there could be. So here, after 9 steps, it comes to just an intermediate product of formaldehyde. So more steps to follow to eventually convert to CO2. So this means, so therefore, in an enclosed container in the lab, so the reaction can happen effectively because there's enough time, and it should be the same under the solar chimney collector. I will show you later. We will have sufficient time when the air passes through the collector. But in the open air, so the interaction between gas molecules and photocatalytic surfaces is just touch and go. So there's no enough time to complete the long series of reactions. So this could result either no effective reactions at all or production of some unwanted intermediates. So this is not only my imagination, but there is an insightful report we can look into. So several years ago, the UK governmental department for environment, the EPA equivalent in the States, so produced this report. The title is, actually it talks about photocatalytic paints and surfaces for removal of NOx, so to remove air pollutions basically. So the background was that in the last 2 or 3 decades, there were lots of lab scale research showed very promising results that photocatalytic paints could be a good solution to tackle air pollutions. So in the UK, in the EU, and also internationally, so there were funded field tests, field trials in the open air, but no significant progress after many years. So they then conducted this review and tried to find out what happened and what's the next. So their conclusions are, so first, at lab scale, this photocatalytic process is very effective. There are lots of data, but poor results in field trials in open air. So because of they observed low efficiency, undesirable, unwanted intermediates, and also very difficult to measure because in the open air. So they recommend some alternative designs needed rather than just paint surfaces in the open air. So this is for the research field for the air pollution only, but it is reasonable to say that paints in the open air would not work effectively for methane removal too. So but in order to reproduce lab results, we need to so we do need to collect and process air in a reactor. So in this sense, so we say that solar chimney is the best and maybe the only solution to do so at a large scale. So of course there are other ideas like what about solar panels plus fans? So or we can combine photocatalysis with other DAC methods. So I will briefly discuss these ideas later. So let's first focus on photocatalysis and solar chimney first. So at this stage, you may still have a doubt thinking that, so there is a fact that methane oxidation does happen naturally in the open air, in the atmosphere. So yes, but this is different comparing to photocatalysis. So the reactions in the atmosphere are called, we call them homogeneous reactions. So there's no involvement of interaction between gases and solid surfaces. So as we already mentioned this natural sink of methane, so I know there are ideas of enhanced nature sinks. So in the open air, actually they have the same challenges to, for example, difficult to measure and control. So and then the public would be reluctant to accept these new measures. So then how about if we apply these ideas under the collector of solar chimneys? So then maybe problems solved. So it is mentioned many times now here, a large scale. So then how large the scale can be. So I can give you 2 examples. So first, for a 200 megawatt solar chimney power plant, so one such tower could remove about 5,000 ton methane per year. So then 50,000 such towers would be needed and would be also sufficient to process the entire atmosphere every 15 years. So reducing methane by about 50, half or 3/4. So that means restoration to pre-industrial level. So after 15 years. So if we need that many towers, so the footprint, the land area we require would be 2 million square kilometers, like similar area compared to Mexico. So if we consider electricity is icing on the cake and we just focus on methane removal, so then we can apply smaller solar chimneys. So for example, the 5 megawatt solar chimneys. So then one such tower could remove about 500 ton methane per year. So then we need 500,000 such towers to process the entire atmosphere in 15 years and restore the methane level to a pre-industrial level. So in this case, we will need a much smaller land area to support those towers. So 500,000 kilo square meters, similar areas than Spain. So yeah, this just gives you some idea about the scale. And now it comes to the next question. So is this solution economically viable? So the short answer is yes, based on the data we have. The cost of 200 megawatt giant solar chimney power plant, it will cost roughly 500 million, 500 million. And if we assume the price of methane removal every ton, it is 1,500 US dollars. So then we can generate a revenue of 7.5 million per year. And we can produce lots of electricity. So for the electricity, we use some data nowadays and calculated the revenue from electricity, 52.5 million per year. And depending on interest rates, it will be 10 to 30 years payback time. But we need to emphasize that for solar chimney power plants, they have long lifetime because apart from the turbine, so the entire structure, there's no any moving parts or very simple mechanical structure. So they can last for more than 100 years. So based on this estimation, we say the short answer is yes. But yes, there are, we need to look into the economic viability alongside some more questions. So for example, what about the comparison between one giant plant versus multiple small plants? What the economics will look like? And what about if we only use them, no electricity production, just use as greenhouse gas removal, or together with electricity? So, and also, what about the earlier idea? So I mentioned if we use solar PV, solar panel, and use this cheap electricity plus a fan to construct a different type of reactor. So compared to this solar chimney idea, what the economics will look like. So these are all good research topics, and my PhD students are working on this, and hopefully I can share more outcomes with you sometime soon. So I'm sure you are having some other questions, like the relatively large land footprint of solar chimneys. It could be too high. And can we apply this solution to remove methane at its sources? So, yeah, we are always thinking the same. And apart from giant solar chimneys, there are other solar updraft devices working in the exact same principle, like ventilation chimneys, trombo walls, and double skin facades. So which have low land footprint and can be applied at methane sources. So for example, we proposed to install solar updraft devices on livestock buildings. So for this idea, one of the early questions is that can this technology be deployed around the globe? So can moderately low solar radiation, like in most European countries, generate sufficient updraft, the airflow? So to answer this question, so we tested this idea using both computer simulation and experiment on a 2-meter high device we built on our campus. So the results show that low intensity solar radiation is not a problem. So 120 volt per square meter solar radiation is already enough to generate considerable updraft. So 100 cubic meter per hour per square meter, the device. So to give you more sense about these numbers, I give you some more information. So 120 volt per square meter, so it's not a high threshold. So it is achievable on 281 days or 1,600 hours in 2020 in England. So we know, so the sunshine here is not brilliant. So even here, so in most days, it is achievable for this solar radiation intensity. And for 100 cubic meter per hour per square meter of solar updraft device, so I took this example. So for a typical dairy house, 1,000 square meter of rooftop area, and it ventilates 18,000 cubic meter per hour of air inside the building, and 750 gram per hour methane emission. So then if we install 180 square meter of solar updraft device, that is only 18% of the rooftop, less than 1/5 installation, can provide the same ventilation rate and remove 50 to 60% of methane emission. So we had this idea founded by Department for Business in Energy and Industrial Strategy in the UK, initially for a design phase. So, and within this funded phase 1 projects, they picked up some of these to continue the phase 2 demonstration. So however, sadly, so they picked up those with very high TRL levels to demonstrate, to support, not ours. So here the related, the TRL levels. So we believe that in this idea, so there are 2 different parts, solar updraft and photocatalysis. So for the solar updraft part, relatively higher TRL level at 6, we believe, and for photocatalysis at 4. And for the funding I'm mentioning here, so they support something higher than 6 overall. So then also besides solar updraft, we also consider the possibility of combining methane removal with other DAC methods. So then again, so one of the fundamental questions is the same. So photocatalysis or other oxidation processes like zeolites or others. So of methane removal. So they all need residence time to complete a series of reactions. So then can we design something which can provide the residence time needed? So they say this will be a fundamental question to answer for this idea. But before answering this question, so we need to find out what the exact residence time is needed to remove, for example, the 2 ppm atmosphere methane. So we built a very simple flow reactor in the lab by adjusting the inlet flow rate, air flow rate. We can test photocatalytic removal rate of methane under different residence time. So yes, slower flow rates give you longer residence time in the tube, in the reactor, and faster flow rates give you shorter residence time. So then we measured a range of data from few seconds to nearly 1 minute. So here are some Carrera data in this table. So 5 seconds of residence time can achieve 20% methane removal, and 1/3 removal under 10 seconds, half removal under 15 seconds, and 80% removal if we can provide 20 seconds of time, and then more longer time will give you higher removal rates. So for the solar updraft devices, I mentioned if we install on livestock buildings can provide, for example, 15 seconds residence time. So that's why I mentioned earlier 50 to 60% removal rate. So, and under the collector of a giant solar chimney power plant, so the residence time can be as long as 10 minutes. So this is why I mentioned earlier. So it is not necessary to have this giant solar chimney if we only want to remove methane. So smaller solar chimney so will do as well. So here now I can summarize. To summarize. So the advantages for this solar chimney plus photocatalysis idea is that it is purely solar driven, and it can be deployed at a climate relevant scale, and it is a controllable and measurable process, which is very important as well. And they have versatile formats, not only for the solar updraft part. Yeah, you can have giant solar chimney or much smaller other ventilation devices. And also for the removal technology, you can combine with this device. There are also other options, not only photocatalysis. So other thermocatalysis or other method to remove methane, you can also integrate it under the collector of a solar chimney or inside any other solar updraft devices. So it can be a very versatile format. I haven't mentioned, yeah, there are many other co-benefits. For example, so the oxidation processes, they can not only react with methane, so other molecules inside the air, when they move alongside, they can all be removed. So for example, other greenhouse gases, non-CO2 greenhouse gases, and air pollutions, ozone, it can also help to deliver these co-benefits. Yeah, TRL levels I mentioned earlier, we believe that it is 6 for the updraft and 4 for photocatalysis. So of course, there are disadvantages. For example, maybe very expensive, and also they are untested at a larger scale, pilot scale. So to address these disadvantages, so the next steps are, so for example, we are doing some technical economic analysis around some of the questions, the comparisons I mentioned before, and also definitely to really test them at larger pilot scale. So to move these next steps forward, we need research funding. At the moment, I have this Horizon 2020 project funded by the European Commission. So yeah, we still have 3 more years to run this project, and yeah, we have many partners working together. And our Chinese partners, for example, Tianzhen here, so they also secured some match funding from the China side to support the research. But this project, this funding is not a very big funding, so less than €500,000. So it can maintain the work in my group at lab scale, or some simulation work or technical economic analysis, for example, this research. However, so the next step to test it at larger scale, so we do need a much larger funding to support this part of the work. So yeah, this is the end of my presentation today. And yeah, thank you very much for your attention. And yeah, we can have questions and discussions.